Hello, this is Miss Nichols, and this lecture is in our electrostatic series on capacitors, or specifically parallel plate capacitors, which are sometimes known as the link between electrostatics and electrodynamics. So it's sort of nice that this is the last lecture in the series of electrostatics, and we're going to take the stuff we learned about this and carry it into our next unit. The essential question is, what is a parallel plate capacitor, and what electrostatic relationships and equations are relevant to these devices? Quick little roadmap for what we're going to go through in this video. Number one, we're going to talk about what is a capacitor. Number two, we're going to talk about how do you design and build a good capacitor. What's the equation for designing a capacitor? Number three, what are some practical uses of capacitors? Why do we care about them? And then number four, what are the equations that we're going to use to predict the behavior of capacitors that we have built? A parallel plate capacitor is just a pair of conducting plates that are attached by wire to some sort of battery or other power source. And that battery acts kind of like a pump. It basically pulls the electrons off of one side through the battery and it shoves them over to the other side. So the net result is we end up with one plate having an intense negative charge that added all the electrons, and the other plate is left with sort of unmatched protons, so that plate becomes equally positive. One plate's negative, the other one's equally positive. It obviously takes work to do this, right? The battery is turning some of its chemical energy into the ability to pump these electrons, because the electrons don't want to be moved from their protons, and also they definitely don't want to be piled all up on one plate. So in order to force those electrons into that configuration, the battery has to expend some chemical energy to create this basic big storage of electrical potential energy in the capacitor. It also makes a uniform electric field in between the plates of the capacitor. We talked about that in a previous slideshow. So sometimes we use the capacitor for energy storage and sometimes we use it for that electric field, and we'll come back to that a little bit. So we measure how good of a capacitor we have with a new variable known as capacitance. We are going to be using the symbol capital C to represent capacitance in an equation, which is a little bit annoying because capital C is also used to represent the units of charge. We measure that in coulombs, but if you see a C in an equation, not in a units, then we're talking about capacitance. The units for capacitance are the coulomb per volt, which is otherwise known as a farad, capital F. Although a farad is a large amount of capacitance, and you much more commonly encounter microfarads, which is 10 to the negative 6th farads. The definition of capacitance, so what makes a good capacitor, is how much charge that capacitor can store per volt of applied potential difference. So that's the battery piece. We attach a specific battery that has a voltage. Battery is able to push electrons a certain energy density, and good capacitors are able to store a lot of charges for the same amount of kind of push from the battery. Here is a screenshot from a FET simulation about capacitors showing I have two parallel plates attached to a battery, and this is a pretty bad capacitor because it only stores a few electrons on that bottom plate and leaves a few protons on the top plate, so it's really not storing up very much electrical energy, and it's not pumping a lot of charges from one plate to the other. Compare and contrast to this screenshot, which is the identical battery, but this capacitor has a lot more protons on the top plate. You can't see the bottom plate, but there would be an equal number of electrons on the bottom plate. So this capacitor stores a whole lot more energy, lots more charges, even given the same battery. So that's a better capacitor. The equation then for capacitance that I would use if I was in charge of the world is C, the definition of capacitance, is equal to Q over delta V. In this equation, the C stands for capacitance. Big Q, this capital Q, is a little different than the little q you've been seeing. They both stand for charge, but big Q specifically means charge on one plate. Okay, so they're not quite interchangeable. The small q is a point charge at a single point in space, and a big Q represents plate charge on a plate. Delta V is going to be the charge on the battery, the voltage provided by the battery. So unfortunately, they give it to you in a slightly different form. I don't know why. They basically have rearranged it to solve for the potential difference from the battery. So this is the same equation, but in a less intuitive format, in my opinion. In any case, the delta V, as I just mentioned, is the potential difference provided by the power source, the voltage written on the battery, and the big Q is the charge stored on each plate of the parallel plate capacitor, and then the C represents the capacitance, or how good the capacitor is. So how do you create a good capacitor? Well, if you look at this picture, one of the things that should jump out to you is the size of the plate. The bigger the plate, the better the capacitor is going to be, because the more charge we can basically store up on that surface. Electrons want to spread out as far as possible in a conductor. Therefore, if you provide them more space to spread, you're able to store more of those electrons on that surface. So there is actually a linear relationship between the surface area and the capacitance. If you double the surface area of your parallel plate capacitor, you're going to have twice as many charges that you can store, and that means twice as much capacitance. Another thing that contributes to building a good capacitor is the separation between the plates. You'll notice in that first example, the bad capacitor, those plates are really far apart. And in the second example, I've moved those plates much closer to each other. The closer the plates are, the smaller the separation between the plates, the more charge we can store up on those plates. The reasoning behind this is that when the plates are pushed closer to each other, okay, the charges on the plates, in addition to being pushed by the batteries, are noticing the charge on the opposite place because it's nearby. And that charge in the opposite plate actually serves to attract more charges to the plates than you would otherwise be able to do. Okay, so because that negative plate is really close to the positive plate, you actually can hold more charges on that plate than the battery could push by itself, because the charges are being pushed by the battery and they're also being pulled a bit by the other plate. So the closer the plates are, the larger the capacitance, the more charges we can store on them. That is mathematically an inverse relationship between distance, the distance between the plates, so that D is the plate separation, and the capacitance of a particular design. So the last design piece that you need to consider when you want to build a good capacitor is something known as a dielectric. A dielectric is something that we shove in between the plates of the capacitor. You'll notice in that first diagram, there's nothing but clear air in between the plates of the capacitor. And the second diagram, there seems to be something shoved in between those plates. That thing in there is known as the dielectric, and it's an insulator. And it turns out that putting an insulator between the plates of a capacitor increases the capacitance as well. So let's talk about why. Well, for starters, you wouldn't want to put a conductor in there, because if you put a conductor in there, then the charges are just going to zoom across that gap, and defeats the purpose of having the capacitor. But if we put an insulator in there, the charges can't flow through that insulator, so they're going to remain on their plates. But why does having an insulator there allow me to store more charges on the plate? Well, the insulator is going to polarize itself, okay? Insulators don't polarize as well as conductors do, but they still do polarize at the kind of atomic level. And that means that the opposite side of the polarization of the insulator matches up with the plates on the capacitor. And so that polarization exerts a little extra pull on the charges to the plates. So the polarized dielectric adds kind of a third force. We have the pushing force of the battery, we have the pulling force of the opposite plate, and putting the dielectric in there adds another little additional pull that lets me pile even more charges up on those plates. So there is another variable in this equation known as the dielectric constant, and it's a lowercase k. And this value is going to basically indicate how much a specific particular material is going to contribute to the success of a capacitor. There will be a linear relationship between K and C, which means the higher the dielectric constant, the better the capacitor ends up becoming. So let's take those three relationships and build a parallel plate capacitor equation. This is what the equation ultimately looks like to describe how to kind of build the perfect capacitor. The left side of the equation, the dependent variable is capacitance measured in farads. On the right side of the equation, you'll see a linear relationship with the area of each plate. So that's just one of the plates that you have to measure. An inverse relationship with the separation between the plates, as we discussed. And then we've got that dielectric constant K. Incidentally, as just a side note, if there is no dielectric, so you just have a vacuum or air, we assume K is equal to 1 for those kind of lack of materials, which means that other dielectric insulators have Ks that are bigger than 1, depending on their material properties. And then the last thing in there is the vacuum permittivity. It's this universal constant. It's a little piece of the Coulomb's constant, as you saw in our earlier equations, but the value of that E naught is 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. It's a terrible unit. So you usually aren't going to actually have to be calculating necessarily anything using this equation. It's more about knowing the relationships, but if you did have to calculate something, that vacuum permittivity constant can be found on your equation sheet. So what are some of the practical uses of a capacitor? Well, number one, we use capacitors to generate uniform electric fields, as we saw in the last couple slideshows. And we'll learn more about why we need these when we move into magnetism. But in any case, there are times when you just need to have a uniform electric field, and a parallel plate capacitor is the way to get it. Number two, we use them for electrical energy storage, kind of like we store up energy in batteries. We can store up energy in capacitors. But the upside to a capacitor is that capacitors can discharge current much more rapidly than a battery can. So if you need a huge blast of current, capacitors are the way to go. We haven't talked about what current is yet, of course, but you may have a sense. And in any case, we'll get more on this when we get to our next unit. So how would you find the magnitude of a uniform electric field in a capacitor that you've designed? Well, there's two variables that are going to tell you overall what the electric field strength is. The first is how charged up those plates are. So what the potential difference from one plate to the other is. This is usually just the same voltage of your battery, because your battery fully charges these plates. But obviously, the higher the delta V, that means the more electrons and protons we've shoved onto those individual plates, the stronger the electric field in between the plates is going to be. So that's a linear relationship. The other variable that's relevant is the spacing between the plates. So let's just imagine we've set up a constant potential. We've got these things at a set potential. But if I move the plates closer to each other, a little proton or electron in that space is going to feel a lot more force, because all of the protons and electrons in the plates are closer to it now. So that means the smaller the spacing for a given voltage, the stronger the electric field is going to be in between those plates. So taken together, we derive this equation right here. This equation specifically is only for calculating the electric field strength in a parallel plate capacitor, because it has to be a uniform electric field. So just make a note in your equation sheet that that's the only application really for this equation. In this equation, E stands for a uniform electric field. Delta V is the potential difference between any two locations in that field. Often we use the plates themselves, because we know that potential, because we've attached it to a battery of known voltage. But you could choose any two locations in between the space as well. And the delta R is the distance component perpendicular to the two plates. So one of the implications of this equation is that for any given delta R perpendicular to the plates, the potential difference is going to change at a constant rate. So if I knew that the top plate had a 12 volt potential and the bottom plate had a negative 12 volt potential, I could divide that space into as many little chunks as I want, and it's going to change potential at a constant rate. The equipotential lines are straight in that region. So if I divide this into 4 chunks and I know my delta V is 24 volts, each of those chunks is going to change voltage by the same amount. So I'd have 6 volts there. I'd have a nice 0 volt potential right in the middle of those 2 plates, just as if these were point charge particles. We have a 0 volt right in the middle. Same thing for oppositely charged plates. And we would have a negative 6 volt equipotential line in between the 0 and the 12. One little note about this, that comment about them being, the distance has to be perpendicular to the plates. So, you know, if I knew that, you know, from location A to location B, the distance moved there is 0.5 meters as it's shown, because that entire distance is perpendicular. So I could calculate the delta V. So once I know E, I can calculate delta V between A and B by using my 0.5 meters. But if I went A to P instead, a diagonal line, okay, I actually would still use 0.5 meters as my distance, because I only care about the distance that I move perpendicular to the 2 plates. And that should make sense when you look at those equipotential lines. I want my change in voltage to be 6 volts either way, because B and P are on the same equipotential line. So it doesn't matter what path I take, and it doesn't matter where I kind of end up on that equipotential. The only distance that matters is the distance that you're moving perpendicular, crossing those equipotentials. It doesn't matter if you also go some distance diagonal. So to that end, if I move from A to D, even though I've moved 0.5 meters, you couldn't plug 0.5 into this equation and get a delta V, because you actually aren't changing voltage at all. So, little summary of what I just said. The rate of energy change between the plates is constant. That means my equipotential lines are evenly spaced in that region between plates. So we actually use that equation a lot when we're dealing with uniform electric fields inside of capacitors. Or even if you don't see the capacitors and you're just told you have a uniform electric field, even if you can't see the capacitors that are causing it, this equation is a really, really useful, relevant one. But if we were told about our capacitor design, we knew that we had a capacitor with a plate spacing of 8 meters, and we knew that there was a 100 volt potential difference as shown in that diagram, you could calculate what the electric field strength for that capacitor would be. So you would just say, you know, E is equal to delta V, which is 100 volts, divided by the distance, which is 8 meters. So I have a uniform 12.5 newtons per coulomb electric field in the space between those plates. But the kind of problem that they typically give you on the AP exam asks if you can stretch and combine this equation with some other equations to understand how particles moving in this electric field would be impacted. So once we found the electric field strength, you can find ultimately the velocity of particles that are released in this electric field. So a sample problem, a particle is released from rest at the red star shown in a 12.5 newtons per coulomb uniform electric field, which we found in the last problem. What would be the velocity of that proton after it has traveled 3 meters? So I've drawn a line in there. That proton, once it's released, is going to move directly to that negative plate, towards that negative plate, because it's, you know, being pushed in that direction by the positive plate and pulled by the negative plate. And it's going to speed up as it moves. So how could we find how much that thing speeds up? Well, it's a series of equations, and if you want to pause the video and try it on your own, that would be totally awesome before I give you the hints. So pause now. Okay, and if you're back, these are the hints. These are kind of the sets of equations I would use to solve that problem. First thing I would do is I would go back to that equation we just used, and I would solve for delta V. I would figure out how much potential difference is there from where the red star is to where it ends, right? So if we plug in our 12.5 volt or 12.5 newtons per coulomb electric field, and we know we moved 3 meters, you should be able to find delta V between those two locations. Then you can figure out how much electric potential energy that proton gained. because electric potential energy is defined as the test charge, which is the proton, times how much voltage it changes by. So you ought to be able to calculate then delta UE for that proton. Remember that Q of a proton is a constant and it's given on your equation sheet. From here, we're going to use conservation of energy. So that proton lost electric potential energy as it moved towards the plate because it did it on its own. That energy has to go somewhere. The somewhere it went to was kinetic energy. So we're just going to take the amount of energy we lost and turn that into kinetic energy of the proton. So then we can calculate the velocity using kinetic energy is 1/2 mv squared. And again, the mass of a proton is a constant from your equation sheet. So happy calculating if you guys want to run through that. Because I'm committed to making sure that you have at least seen all of the equations that are on your equation sheet, I'm going to talk about this bonus useless equation. I don't know that I've ever seen this equation applied on a test, nor can I really imagine why it would be applied. So maybe you can tell me why this is useful. That would definitely earn you some candy in class. But here's an equation that's given. And I can derive this equation from a random combination of other equations. It basically says the electric field strength, uniform electric field inside a capacitor, is equal to Q, the charge on one of the plates, divided by the dielectric constant times the area of the plates. So I can algebraically explain this equation, and theoretically this would be useful for calculating the electric field between those plates if you happen to know the charge of the plates and the area of the plates. But functionally, this is not a very useful equation because it's way harder to find Q than it is to find voltage, for example. I don't have a machine that can count up the number of charged particles on a plate. So to me, unless you really wanted to know how many charged particles were on a plate, this equation is not super useful. However, here's some fun bonus questions to ask yourself. Can you think of some really useful application of this equation that I don't know about? And I would love to hear about it. The second fun bonus question is, what happened to K during the derivation of this equation? So if you want to go back and figure out where this equation comes from, the K actually disappears somewhere, that dielectric constant. So if you want to explain to me where that went, I would love to hear it from you. I know the answer, but it's kind of a fun thing to think about. Okay, so the last equation we're going to define for this entire unit is for the total overall amount of electrical potential energy that a capacitor can store. And so this would be, if we didn't really care about the electric field, but we wanted to use the capacitor as an energy storage device, how much can we store? So this derivation comes from the fact that every time you move a charge from one plate to the other, it requires work. The battery has to put some energy into doing that. And each charge moved requires progressively more work than the last one because the space on those plates gets more and more crowded, and the first electrons start pushing back on the additional ones that the battery tries to move. So this is really a calculus situation because the amount of force, the amount of energy grows with every addition, with every dq, if you will, if you're in calculus. So I'm going to do just show just the bones of the derivation, just for those of you that are in calculus. But if you're not in calculus, you can just watch it for fun, and then we'll get the equation near the bottom of the page. So this is my basic definition for capacitance. C is Q over V, rearranged to be for V, like they gave you in the equation sheet. And we're going to combine that with my sort of definition of electric energy as the voltage times the charge. And we're going to think about this as, instead of changing voltage, we're actually changing the charge, because each time we throw a new electron from one plate to another, that charge is growing by a little bit. So we're basically going to write this in a calculus kind of form as UE equals V dq, and then we're going to replace the V with Q over C from that first equation. So we end up having this integral for the total amount of electrical energy stored up on a capacitor, which is Q over C, or integrating from 0 to Q. So 0 is no charge on the plate at all, and big Q is the final charge that the plate accumulates, of the function Q over C dq. So if you're in calculus, go ahead and do that integral just for fun. And if you're not in calculus, then we can skip ahead to the result, which is UC, which is the electric potential energy stored on a capacitor. So that subscript indicates that we're only using this equation for capacitors, equals 1/2 of big Q, which is the charge stored on a plate, times the potential difference between those plates. You can also take that original V equals Q over C and substitute in for the Q in that equation algebraically. That gives us this second half of this equation, which is if I plug in a Q over C, then I get 1/2 C times delta V squared. So just as a final little bit here, reminder that UC stands for the electrical energy stored in a fully charged capacitor, and we measure that in joules. Q is the charge on each plate of that capacitor, and delta V is the potential difference applied between the two plates by the battery. Or if the information that you have in the problem pertains more to what is the capacitance of the capacitor, because like I said, it's actually really hard to measure Q. It's much easier to measure C or V. We will often use the second half of the equation instead, which is UC equals 1/2 times the capacitance times delta V squared. All right, that's it for equations. That's it for this big meaty derivation. So take a deep breath and go ahead and revisit your essential question, which is what is a capacitor and what are all of the electrostatic relationships and equations that are relevant to these devices? Thanks for watching.